they occurred when we introduced a new technology called fracture mechanics. I mean, it goes a bit beyond fracture mechanics. And within our history in the U.S., the first use of fracture mechanics as a requirement was in the design of the space shuttle. The first use in the U.S. Air Force was in the design of the B-1 bomber. And so we had simultaneously two organizations that were very powerful that were incorporated. Now at the same time, or shortly after that, the nuclear industry began to use fracture mechanics as one of the design principles, and it varied by the organization. But for the first time, we now have an integrated task where we have the materials involved, and we must not only be concerned with whether the material that is coming in the door and the material that I'm inspecting is correct or meets some minimum standard. We also have to worry about the way that material degrades when I put it in service. So failure, graceful failure, is a big concern in the way we apply our materials. We also have to look at the damage modes for the material that I'm putting into service. And the damage mode will depend not only on the way it is used, but its response to the way the material will degrade. It depends on the environment that I'm going to be using it in and a whole lot of other things. But the only tool that we have to say, indeed, I have a crack or I have a crack starter, this is the usual long-term outcome of damage, is non-destructive evaluation. And so we can go sprinkle some non-destructive testing on each of those problems and go away and forget about it, but not quite. Simple standpoint, I want to keep or embed in your mind that the fracture characteristics of a material, or the ability of a material to sustain a crack of a given size under a given load in a given environment, is a quantifiable property. Now, you know inherently that glass is brittle and iron is tough. We've all fatigued barbed wire back and forth before it broke, but the characteristic can be quantified that describes that property of the material, and that's the fracture toughness of the material. So what I've shown is a simple graph that charts the crack size, the stress level in a static case, so that the higher the stress level, the smaller crack that can be tolerated, or I will have catastrophic failure. Now, along with that, we had some very creative thinking, and we are still going forward with a lot of that. We had something called retirement for cause. The concept is that if I have a component that comes out of the factory brand new, I have inspected it, and I know what size flaw I am inspecting to in the factory. Now I have to put a number on my inspection. And I put that into service. And I've gone back and done my calculations in terms of crack growth rate. And I know what my loads are. And I can perform an inspection at some time before the component should fail. And by convention, that inspection interval is typically half of the calculated life before I would have catastrophic failure. Now, materials behaving and the environment that we put it in are not all uniform. So we're not all red-headed in this room, we're not all dark-headed. Some of us don't have any color on the hair, any more left. initiation of fatigue naturally, we get a rather large or long service life where we have some components in that lot that will start to initiate a crack very early in the life, and then others that will go many lifetimes before I need to be concerned about it. But if I apply this technique and inspect and can have some confidence that I have removed all the flaws larger than some value, then I can continue to use that part. And I can calculate the crack road from that size to the next inspection interval and re-inspect. If I don't find any cracks, I can put it back in service. And the concept then is you continue to inspect until you discard it, but you throw it away just before it breaks. And with something as complex as an aircraft, or as complex as one of the components of the aircraft, that's not a bad philosophy. There are a lot of other things that have to go into it, but that's one of the ways that allows us to extend the lifetime of an aircraft and have some confidence that we can get there. Now, I drove over because I'm afraid of airplanes, and but if you ride a commercial airliner, the airliner that you ride on most often is in its second or third lifetime, and this is the only way we are able to provide confidence that we have safety to continue to do that. So this is one of the things. Now the thing that I am most often quoted with is when you do an inspection, if I ask you what size flaw you can find, and you're my best inspector, you will tell me I found a flaw that was equal to a gnat's eye. And it's not important the smallest flaw you've ever found. What's important is the largest flaw you've ever missed. The other thing that goes along with that is the supervisor in the area rarely knows who his best inspector is. As a matter of fact, the best inspector that he thinks is the best inspector is quite often the worst inspector, because he's the guy that's putting out the work, or he's doing it faster and he's stamping off things, causes no problems, because if you identify something, that can be a problem. Now, the flip side of that, you also have to be concerned with false calls, and I'll talk a little bit about that as we go down the line. The smallest flaw you've ever found is not important. It's the largest flaw you've ever missed. Now, we get back to this fracture mechanics thing. This is a failure from an actual aircraft that had a crack starter right. This is not going to work on this color. I knew it wasn't. Crack started at the chamfer, or the change in section at the root of that fastener. You can see it? I can't see it. Okay.
You can't tell where you point, but we can.
Okay.
Yes.
So the crack started right there. Now it grew stably, as cracks do under the right conditions. So it got to this point. And at that point, we probably had a jet jock who overloaded the structure, and the crack took a jump. And the crack